Hi again. So we are going to talk through Unit 7 and look into t-test, which is something that we haven't talked about, right? Or t-scores, because so far we've just been talking about comparing means and samples and our overall populations, and we've had normal distributions. So now we're going to talk about something called a t-distribution. So let me share my screen again, because I feel like I just talked to you, but obviously this is the beginning of the lecture. All right. Take home. All right. So 2317, lecture number 6. Remember, in the last lecture, we learned how to answer research questions by translating them to statistical questions. And we either used our confidence interval, the 95% confidence interval for mu, or we made the hypothesis testing, right? We had these two competing models, and we were computing probability that way by observing a particular sample mean if our hypothesis, our null hypothesis was true. Remember that H0 was our null hypothesis and H1 was our alternative hypothesis. But maybe you noticed that in every example all semester so far, we have known what the standard deviation is. But what if we don't know what the standard deviation is? What if we don't have sigma? Then what do we do? For example, a population has a mean of 23. A sample of n equals 4 is given as an experimental treatment and has scores of 20, 22, 22, and 20. Does the treatment result in a significantly lower score? Well, we don't have sigma, so how are we going to figure that out? We can't do any of the formulas that we've been doing yet or before because we don't have sigma. So we're going to introduce this new concept where we estimate sigma. So based on the information that we have, we can estimate it, and we'll call that sigma hat. But this formula here is how we would do that. So take a look at it, and then let's look. If we estimate it using the formula that we already have, it systematically underestimates what sigma is. So we have to do something to compensate for that. We have to do something to fix it underestimating sigma. So if it's underestimating it, we need to kind of inflate the numbers the opposite way. So we can do something called sigma hat. So it's denoted like this. It's got the sigma sign still here. I guess you can't see it. I'm pointing, but I don't know if you can see that. With the hat above it. So this is equal to the square root of the sum of squares divided by n, which is like the formula we've already seen at the beginning, but it's n minus 1. When we have to estimate the standard deviation, our original standard deviation formula systematically underestimates sigma, tends to be too small for a lot of reasons that we're not going to talk about in an intro class. But we're calling this n minus 1 degrees of freedom. So that's an important term that you'll need for this class. You'll need it for research methods as you move on in our psychological studies. So remember that degrees of freedom is n minus 1. This is the technique for at least partially accounting for error in our estimation. So this fixes it. So we've gotten used to calculating z-scores and comparing our z-scores to the distribution of z-scores, but we can't use z-scores when we have to estimate sigma or when it's unknown, because when we estimate it, this relies on our sample size, more specifically on degrees of freedom, which is n minus 1. So since this estimation method produces a distribution of z-scores, this is no longer normal. So what we've been seeing so far is our normal standard distribution, right? Our normal typical bell curve. But now that we're estimating the distribution that we're getting, our z-scores, they're in parentheses or quotation marks here because they're not technically z-scores anymore, right? It's no longer a normal distribution. It looks a little bit different. So we need a different distribution. We're going to call this student's t-distribution. That accounts for when the degrees of freedom have the calculating probabilities. We're calling this the t-distribution. And luckily, it's built into that psychological statistics app, web-based program calculator we've been using. So no worries. We've always been clicking normal. When you just get to click T. So back to our example, now that you know this information, Our population has a mean of 23. A sample of n equals 4 is given an experimental treatment, and then they had scores of 20, 22, 21, and 20. Does the treatment result in a significantly lower score? Let's find out. So let mu be the mean of the treatment population. So that's here, that's given to us. Population has a mean of 23. And then note that this mean the X bar is 21, and you can get that by adding 20, 22, 22, and 20 and dividing by 4. So for our null hypothesis, mu is equal to 23, right? We're assuming that there's no change. So there's no difference in our scores. Mu is going to be the same as it was originally with the population, which was 23. But our alternative hypothesis says that maybe mu is less than 23. Maybe we saw a significantly lower score after we gave this treatment. Remember that our null hypothesis should be written with some form of equality, right? Mu is equal to, it's less than or equal to, it's more than or equal to. And then our alternative hypothesis should be written using not equal to, greater than, or less than. So we're going to do what we learned last time in our hypothesis testing. We are going to assume that the null is true. We're going to assume that our treatment had no effect. So we're going to find P of X bar less than 21 if HO is true, if our null is true. So we need the sum of squares, and then we need to divide that by our degrees of freedom, and then take the square root to get sigma hat, right? This formula here is sigma hat. So we already know how to do the sum of squares. We relearned that at the very beginning of our class. So we'll take our four numbers, and we have 20, 22, 22, and 20. And then that gives us X bar 21. So now we're going to subtract that from each number. So 20 minus 21 is negative 1. 22 minus 21 is 1. 22 minus 21 is 1. 20 minus 21 is negative 1. So right, that'll equal 0 just as a check. And then we look here. Now we're going to square it. So in this case, it's 1, 1, 1, 1 all the way down. So we know that our sum of squares is equal to 4. So for sigma hat, the formula is the square root of sum of squares divided by n minus 1, or degrees of freedom, since n minus 1 is degrees of freedom, equals square root of 4 divided by 3, which equals 1.15. That's what we just did. Now we have sigma hat. So now we can compute our t-score. The formula for a t-score is the same as the formula for a z-score, except that instead of using sigma, we're using sigma hat. So t equals X bar minus mu over sigma hat divided by a square root of n. And remember, this is like our standard error, right? But instead of sigma, it's sigma hat. So for this particular example, you can see how we divide it out. We get negative 3.48. So now we're going to put that into the SciStat calculator, but instead of choosing normal, we're going to choose t. And then we have our degrees of freedom. So that's important because now we're saying this is not a normal distribution. So it needs to know information to figure out what the answer is. So you always need to have the degrees of freedom. So you just take whatever the number is, minus 1. And that's where you'll plug in the degrees of freedom. For this example, we're using lower tail because we're seeing if it's less than. Negative 3.48 means we got P equals 0.02. And since we were saying that our threshold, we learned that in the last semester or last lecture, right? The threshold for significance is 0.05. If it's less than that, we say that our data is very rare if this is true, right? 0.02 is very rare, right? That's really small. That's smaller than 0.05, which was our threshold. So we're going to reject the null hypothesis in favor of the alternative hypothesis because mu was less than 23. We're going to conclude that the treatment results in significantly lower scores. Hooray! Our treatment worked. We found significantly lower scores. That's it. That's a lot of words. You can watch this a couple of times. You can look for other resources. Definitely read the section in your textbook about it. But that's all it is, right? That's how we dip our toe in the water of t distributions. There is this idea, or not idea, there's this other thing called paired samples or paired samples t-test, or could also be called a repeated measures t-test. And that's just where instead of comparing our sample mean to a population mean, we're comparing participants to themselves. So that's when one participant is measured on two separate occasions. So they're being compared to themselves instead of some larger population out there. So we would compute the different scores for each participant. So their score minus their next score, and their different score is what replaces x bar minus mu in the t-test formula. So instead of x bar minus mu, it's TD, like the different t-score is equal to XD divided by the standard error. So for an example of that, if we had a study of N equals 9 individuals, they're participating in a repeated measure study where their critical thinking performance is measured twice. Once before engaging in a critical thinking training task and a second time after they received some training that we came up with. Then their sample mean difference score, say, was x equals 12 with a sum of squares of 360 for the different scores. Is the mean difference score large enough to be considered a significant increase in critical thinking performance? Well, what do we know? We know that n equals 9. We know that the difference is 12 between the first and the second, and the sum of squares is 360. And what do we want to know? We want to know if x bar, the difference score, is greater than 12, significantly greater than, right? So we have our two competing hypotheses, the null that says the difference is less than or equal to 0. And we have our alternative hypothesis that says, no, it's greater, it's significantly bigger than no difference. So step 2, since we don't know sigma, we estimate it, so we need sigma hat. So we do our sigma hat formula, and we get 6.708. And then we can calculate our standard error because we need that for the t-test. So we can compute standard error based off our sigma hat, which gives us 2.236. Then we can calculate the t-score because now we have those formulas, and we replaced it right here with x bar d, which gave us 5.367. And then we plug that into the app. Distribution is t. We have our degrees of freedom, which we had 9 participants. Our n was 9, so our degrees of freedom is 8 because it's n minus 1. We're going to choose the upper tail because we're trying to see if it's greater than. This gives us a t-score of 5.367. So we can say that t was t greater than 5.367. And it equaled 0.0003. Well, that seems like it's way less than our critical value, right? That we've just decided upon, right? It's just psychological fact, right? 0.05, less than that equals significance, right? So because 0.0003 is less than the critical area of 0.05, we can reject the null hypothesis and we can conclude that our critical thinking scores were significantly increased. They were significantly higher following our training, so our training worked. But instead of comparing our students to some general population, we compared the students in our experiment to themselves before the training that we gave them. So take home, what did we learn? We learned that when sigma is unknown, we can estimate it from the data that we have. When we estimate it, sigma hat, the distribution of sample means depends on the sample size, specifically the degrees of freedom, which is n minus 1. Then we can perform a t-test. And then we learned about single samples versus paired samples. That's it. That's all we did. So now you know the basics of everything you need to know about t-testing. So that's it. Email me if you have any questions.